So we've been looking at the average rate of change. So that's just giving us what's the slope between 2 points. So that's giving us an average of what's happening with that function between those 2 points. But maybe we want to know what is that rate of change exactly at some value on our function. And that brings us to what the instantaneous rate of change is. So let's kind of look at a picture of what's going on. So let's say we have some graph of f of x. Look like anything. And what we were just doing is, hey, if I have some value in here, a, and we have some value over here, let's call it a plus h. So basically all I'm doing is taking this value a and I'm adding some value h here to a to get my next x value. So if I do that, right here, this would be f of a. And right here, this would be f of a plus h. And we were just looking at the average rate of change between these 2 points. So the slope of this line. So again, let me write that down. So if we were looking at the average rate of change between those 2 points, it would be the change in my y value. So notice my y value for the first point that I'm going to use is f of a plus h minus the other y value, which in this case, I called it f of a, all over the x value, a plus h, minus the other x value, in this case is a. And so if I simplify this, I notice that my denominator, I have like terms down there, a and negative a. So those actually cancel out. So notice that this is the same thing, reducing it as f of a plus h minus f of a all over h. So we've been talking about limits, and we needed to talk about limits in order to get this concept down. Well, if we want the instantaneous rate of change, we don't want this value of h to be very big. We want it to be as small as possible. Because if we keep on choosing values of h that are smaller, so for instance, if I came over here, this would give me a better representation, what the slope is there between those 2 points. I'm trying to figure out what the slope is at x equals a, but if I make my h value even smaller, so I really want this h value to go to 0. That distance between a and that next point we're going to choose, we want it to be so small, infinitesimally small, that it basically tells us what that slope is at that point. So we want h to go to 0. That distance between the 2 points we choose is so infinitesimally small, it's going to give us the instantaneous rate of change. Then we get the instantaneous rate of change. Okay, so there's our formula. So for instantaneous rate of change, at x equals a on a function f of x is given by the limit as h approaches 0 of this f of a plus h minus f of a all over h. Okay, so let's look at an example of that. So it says find the instantaneous rate of change for each function at the given value. So let's say that we're given that f of x is equal to negative 4x squared minus 6. And we want to find this at x equals 2. Okay. Okay, so our a value in this case at x equals a, our a value in this case is 2. This is where we want to go in and we want to figure out, and maybe let's do this in pieces right now. Let's first look at what is f of a plus h. Or in our case, let's figure out what is f of 2 plus h. So that means we have to go into this function, f of x, and wherever we see the x, we're going to replace it, instead of just a number, we're going to replace it with that expression 2 plus h. And so doing that, we have this is equal to negative 4. I see an x there, so I'm going to put parentheses big enough to write in 2 plus h. That squared minus 6. So this is negative 4 all times the quantity 2 plus h, quantity squared minus 6. Okay, so we have to be careful because that 2 plus h quantity squared, that's telling me I have to take 2 plus h and multiply it by 2 plus h. So let's do that first. Let's maybe distribute this out before we distribute the negative 4. So let's keep the negative 4 outside and then distribute. So 2 plus h times 2 plus h. Well, 2 times 2 is 4. 2 times this h, so plus 2h. Distribute the next term inside the first parentheses. So h times 2, so plus 2h. And h times h, so plus h squared. Close our parentheses, and then we still have that minus 6 here, so minus 6. So before I distribute the negative, let's combine like terms inside our parentheses. So recall like terms, they have to both have the same variable and they have to be raised to the same power. So only like terms in here are the 2 h's. So 4 plus, well, 2h plus 2h, that's a 4h plus h squared, and then minus 6. So now let's distribute the negative 4. We get negative 4 times 4, so negative 16. Negative 4 times 4h, so minus 16h. Negative 4 times h squared, so minus 4h squared minus 6. Again, I notice I have some like terms in here. So negative 16 minus 6. And I'm just going to rewrite this in descending order of powers. So my first term I'm going to write is negative 4h squared minus 16h. And then negative 16 minus 6 is negative 22. Okay, so that was just this first piece of that limit. And then it says, let's look at negative or minus f of a. So this is saying I'm taking a negative 1 and I'm going to multiply it by whatever f of a is. In our case, again, a is 2. I'm going to have this negative out here. I'm going to have parentheses. And now let's go in, and wherever we see an x in this f of x function, we're going to put a parentheses and then replace it with 2. So I have negative 4. I see an x here, so let's put parentheses, quantity squared, and then a minus 6. So simplify it down. So the negative out front, I have a negative 4, and then 2 quantity squared is 4. So negative 4 times 4 minus 6. So negative outside the main parentheses. So negative 4 times 4 is negative 16 minus 6. So negative of negative 22, which is 22. So now let's kind of put it all together. So I'm first going to write my limit as h goes to 0. I'm going to write my f of a plus h piece, which we found to be this. So negative 4h squared minus 16h minus 22. We're now going to subtract off f of a, or in our case, we already did that. So really we're adding, because this is positive, plus 22. Because we already did that minus. And now we have to put this whole thing all over h. All over h. So notice we have some like terms in our numerator. So I would go in and I would simplify before I plugged in my h value of 0. So we have negative 4h squared minus 16h, but negative 22 plus 22, those cancel, all over h. Notice if we did do direct substitution right now, we would get that indeterminate form. We would get a 0 on the top and a 0 on the bottom, which tells us that it doesn't tell us anything. But also notice that we can factor an h out from both of those terms on top. So let's factor out an h. If we plot an h there, the limit, h goes to 0. If we factor out an h, you're left with negative 4h minus 16 all over h. And notice those h's cancel in the numerator denominator. So really we have the limit as h goes to 0 of our numerator, what's left, which is negative 4h minus 16. Now let's go in and do our direct substitution. And so wherever you see an h, we're going to plug in 0. And so we get negative 4 all times 0 minus 16. So negative 4 times 0 is 0 minus 16. So this is negative 16. Okay, so I know when we looked at this, if we look at this function, and I'll pull up the graph in a second. Let me just pause because I see you guys have some questions or something's in here. Okay, so I just graphed our function, which I just lost. And we were looking at the instantaneous rate of change when x is 2. So if you come on here and let's look at when x is 2. So it's about here, right? Notice that your parabola is facing downwards. This is decreasing here. And it's telling us that it's decreasing at 2 at a rate of, what did we just find? Negative, I forgot, 32 or something. Negative 16. Get out of there now. So looking at the graph, we can see that it's negative, that the negative is decreasing pretty far. Pull it back up. I don't know where it went. Okay, so if we looked at the graph and we decided we wanted to find the average rate of change here around x equals 2, we could plot points that were really close to x equals 2 and find that slope between those 2 points. And that's what we were doing with the average rate of change. And you'll see that the closer you choose your value to x equals 2, the more your slope is going to look like the negative 16 there. Let me go back and let's kind of do that and show that. That's what we would get. Okay, so I just went back to Desmos. I'm using their scientific calculator tool. And so this is going to be helpful sometimes when you're doing some of the homework to use this feature. So you can go in and you can define your function f of x. And now I want to look at the slope as we're getting closer and closer to x equals 2 to see, is that looking like it's really negative 16 there? And so first of all, let's look at the point when x is 2. Let's figure out what our y value is. And so we can do that by looking at f of 2. And notice in here we have the result of negative 22. So we have a point when x is 2, y is negative 22. And so let's look at something even closer or close to that value. So if I looked at f of 3, that's negative 42. And that's not going to give me as good of a value, but 3 is negative 42. Let me just write these down. Let's look at, instead, let's choose something that's even closer to 2 than 3. Well, 2.5, that would give us something closer. So at 2, I have 2.5. Actually, let's go in here. We can even do this. Let's define our function next. Can I do this? How about g of x? I've never done this before. Maybe it will work. This would be cool. Let's put in what the slope would be for f of x. So this would be, how about our top function? It's our change in y. So let's do f of x. I want to look at the change in y always at that point to negative 22. So let's put in our y value there. So minus negative 22. So really plus 22. In my numerator, that was the change in my y value, all divided by x minus my other x value, which is 2. Okay, so that's basically the slope between some point I'm going to choose and that point to negative 22. So let's look at what that slope would be if I looked at g of 3. So that would be between the point 2 and 3 on that function. is negative 20. Let's look at g of 2.5. So notice that slope is negative 18. Let's get closer to 2. So let's look at f of 2.2. That gives me negative 25.36. How about f of 2.1? That's giving me negative 23. 2.00001. That's negative 22. Did I not? Or how about f of 1.9? That's negative 20. F of 1.9999999. So I'm looking and I'm wondering if I come back here. Found the slope wrong. Because we found the slope was negative 16. So that's what we should be getting as h is going to 0. So just want to make sure my work was right. Actually, this is minus 22 right here, but those added. Okay. Pause. Okay, so we figured out what was wrong. I was putting f instead of g when I had done our slope to be. So notice g of 2.2 is negative 16.8. G of 2.1 is negative 16.4. And now if I put in g of 2.001, notice this is getting closer and closer to negative 16 as we're like taking the limit and we're coming closer on the right-hand side. And so let's see what's happening as we come in the right-hand side of 2. So if I plug in g of 1 point, left-hand side of 2, 1.9, I get negative 15.6. But if I even get closer on the left at 1.99999, notice that this is negative 15.99996. So notice this is both are getting closer and closer to negative 16 as we're approaching it on the left and the right. And so it doesn't matter how close we get it, or the closer and closer we get it, the more you're going to get equal to 16. And what's happening right here is they're rounding and they're getting that they have a 0 in the denominator. That's why it's saying it's undefined. But as I said, they're getting closer and closer to negative 16, which was the instantaneous rate of change of that function at x equals 2.